So let's talk about how do we actually solve systems, model systems of differential equations. We're not going to talk about solving them yet, but we're just going to talk about how we model systems with differential equations. And there's lots of different types of systems you can have with differential equations. We're going to just talk about two of them. And what we'll do is we're going to look at whether when we have competing objects and you can get a system. Now these are competing, but you can also get ones that are cooperative systems, cooperative objects. So you'd have basically the same type of structure if you have cooperative objects or competitive objects. You have a derivative, the rate of change of one of your population values or one of your objects, x we'll call it, which is one function that's of x, t, and y. And you have another rate of change of your y function that's a different function that's t, that's involving t, x, and y, where t is your independent variable. So we want to look at how this would do and what we would look at this. So let's take an example. Before we do an example, sorry, let's just talk about what it would look like if your system is linear. So if your system is linear, it just means that your two g functions, that are functions of x, y, and t, these are the functions that your rate of changes are equal to. And so if you have c1x plus c2y plus some function of t, notice the x and y are to the first power, so they are linear. I don't care what f1 of t is. It could be a nonlinear equation, or a function, I should say, but it's just involves t, doesn't involve x and y. The pieces that involve x and y are linear. And the other function, the other rate of change is equal to g of t, and that's c3x plus c4y plus some other function of t. And again, the x and y are to the first power. So that's what makes them linear. And so let's look at an example of what this would look like, of how we talk about these. So let's consider the competitive model defined by dx dt is equal to x times 2 minus 0.4x minus 0.3y. And dy dt is equal to y times 1 minus 0.1y minus 0.3x, where the populations x of t and y of t are measured in thousands, and t is measured in years. And what I'm going to do is we're not going to learn how to solve these per se, and we're going to talk about how we come up with these models. What these models are talking about is how x and y are related to each other. This one is linear. We can also have ones that have x times y, and that would be an interactive term. These don't have that interactive term. And so we're going to look at what these do, but you can also have ones that have an interactive term. These two are linear, so they don't have that term. And these come from, usually we come up with these equations by doing some kind of collecting of data to see what's happening to x and y as over time, and usually seeing what's happening to these two different populations. Then we can come up with these two equations that we'll talk about it. T is in years, and we're going to use a numerical solver to analyze what happens to this population over a long period of time for each of the following cases. So we're going to look at 4 different cases. The first case, each one of these is where time is 0. We're giving you the initial condition. One of them will be that there'll be 1.5 thousand of your X population and 3.5 thousand of your Y population. That would be one to look at. A different one would be 1 and 1 that we'd have of each one, 2 and 7, and 4.5.5. So these are the 4 different scenarios we're looking for, and we're going to see what they look like. We are going to use a numerical solver to do this. So I happen to like the site, Bluffton University site on this. So Bluffton University has this wonderful script for doing these. There's lots of other ones out there that exist. We're going to switch this over to system. Notice our systems are dx dt and dy of t. In the x, you can type in what x was equal to, and I believe it was 2 times, and I always have to go look. 2 times, I'm sorry, x times 2. I knew there was a 2 somewhere. So x times 2 minus 0.4x minus 0.3y. And then we're going to do the exact same thing with the y one and go look and see what that one was. And the dy dt was y times 1 minus 0.1 y minus 0.3 x. Okay, so I like to compare, make sure I do have the right ones down. So I have x times 2 minus 0.4x minus 0.3y, and y times 1 minus 0.1 y minus 0.3x. So I do have them correct. I'll hit enter. And this is what the slope field would look like. I don't really need, because these are population values, I don't need the negatives here. So we're going to go ahead and change our window a little bit to have x go from 0 and y go from 0, just because we don't need the pieces, and see what we look like. Now we can find out where each of the initial points are and just click on it, or it's easier just to type in those values. So our initial conditions, one of the ones we're going to look at is x is 1.5 and y is 3.5. So I'm going to type an x of 1.5 and a y of 3.5 in here, and then I can look to see what happens to it. So basically it's going to find 1.5 here on the x, 3.5 here on the y. So this is the x-axis, this is the y-axis. And so we come over here, 1.5 on the x, 3.5 on the y, and then we're going to follow and see where this takes us, where this graph is going to go. And so again, I'm going to let the technology do this for me. Oh, I need to go up higher. Let's go up to 10 in the x and 10 in the y. And then we'll submit this. And now we can see what this graph looks like. So one of the things I noticed is we're starting up here, we're following along this curve, and then we suddenly get to this kind of asymptote, a slant asymptote here. But notice what is happening as we're traveling along here is the x value, again, this is my x-axis, this is my y-axis. My x values are getting smaller and smaller and smaller. In fact, they're heading to 0. But my y values are getting bigger and bigger and bigger. In fact, they're heading to infinity. So we can actually say in here that as t is increasing, because we want to know what's happening on a long period of time. So what we can say is as t goes to infinity, x is going to nothing, to 0, but y is going to infinity. In other words, it means that, and probably not going to infinity, but it's just getting larger and larger and larger. It just means that your y object, whatever it happens to be, your whatever that population is, population of some kind of animal, that's getting really large, whereas the other one's going away. So let's look at what if x is 1 and y is 1 at time 0. So we'll change these to 1 and 1. Submit that one, and now we can see we come over here to 1 and 1 on the y, and we start following along the slope curve. And again, we're coming along this asymptote. And so what we can see is happening is that y is going to 0, because remember, this is the y-axis. So anything down here means we're down at y of 0. I'm assuming the x is getting really, really big. But it may not be. It might just be here the y is going to 10. It might be here the x is going to 5. But we don't really know because we can't see enough of the graph. So we can just assume it's just getting larger and larger and larger. So we can now say on this one that as t goes to infinity, the x is getting bigger, but the y is going to 0. Now let's look at a situation. So it depends on how many you have. So here we have equal numbers of both of them. They're probably competing with each other, in which case they're probably eating off the same food source. So here the x is able to compete better than the y, and the x is able to eat more food than the y is able to eat, and so therefore the x is able to flourish, whereas the y can't compete with the x and dies off. Whereas in this one up here, part A, we have some more of the x, but not as much as we have the y. We have a lot more of the y, which means the y can take over and eat a lot more of the food source, and the x can't get as much of it, and that's why the x dies off. Now let's try this one where x is 2 and y is 7. I would think because this one where the y was higher, y went to infinity, I would assume that this one's going to be where the y is going to go to infinity again. But let's see what happens. So we're now going to change this to 2 and 7, 2 for the x, 7 for the y. And again, what we're doing is we're coming over here, 2 for the x, 7 for the y. And we can see that we start off here, we follow this curve along, and then suddenly the y is going to take off and the x doesn't. So again, what's happening is that the x population, whatever that happens to be, is not able to compete with the y. So the x goes to 0, the y is going to get bigger and bigger and bigger. Again, with this last one, I would assume that because the x started off bigger, that x would now take over. I don't think that's always the case, but it seems to be the case that when the y is bigger, the y takes over. So maybe when the x is bigger, the x will take over. So let's just see what happens. I forgot what those values were. So it's x of 4.5 and y of 0.5. Now this one, you can't really see anything because 4.5 and 0.5 is like right here. So we don't really know exactly what's happening here. So it might help to clear all of our curves and submit this one again. So when I do that, I'm noticing, oh, the x again is probably going to get bigger here. Again, I'm assuming it's staying along this line. We just can't see what it's doing. But the y is going to 0. So it does look like if the x is higher, the x takes over, and if the y is higher, the y takes over. When they're equal, like in this one where they both were 1, the x still took over. And again, the x and y, we don't know for sure that they're going to infinity here. It's just we're saying they're getting larger. Another application of systems is using circuits, looking at what happens in electrical materials. We're going to use what we call Kirchhoff's laws. Kirchhoff's laws come to us from physics. And these are some laws that you study in a physics class. And the first law says that your current in is equal to current out at any branch point. So at any point along that circuit where your current might split, the current coming into that point and the current going out of that point have to equal each other. The second law is that the sum of the voltage drop around any closed loop is always 0. And we've used this one already once, but this is a very important rule and helps us out. So let's go ahead and look at a circuit. This is known as an Lrc circuit because it involves an inductor, which stores the current, a capacitor, which stores charge, and a resistor, which resists the current moving. And it has a voltage source, we're calling it E. Now what happens is you come out of that voltage source and you start traveling along. And so this might be your current. So we like to put down the current of where it's going. It's going to come through this inductor and it's going to come to this point here. And at this point right here, some of it's going to go through the capacitor and some of it's going to go through the resistor. Well, the problem is that it's splitting. So this is not, both of these are not I, they're splitting. So they're different I's. So let's call this one I1 so we can split it. I1 comes along, it comes to this point, and some of the I goes this way. We'll call that one I3. Some of the I goes this way. We'll call that one I2. And so we can see what's happening here. And then when they come around here, I2 is going to come around, come to this point here. I'm sorry, I3 is going to come around. I2 is going to go down this way and come to this point, and then they're going to come together and go back to becoming I1. So this is my circuit. Let's see if we can't. And there are more complicated circuits that exist out there. Have more resistors, have resistors that are branching. We're going to look at a fairly simple Lrc circuit right now. And so let's see what happens. That I is coming along. So we have I1 coming along. It's going to come to this branch point, and Kirchhoff's first law says the current into a point is equal to the current out. But the current out split. So these two currents together have to equal this one current here. So current 1 has to equal I2 plus I3. So there's one relationship between our currents. That's great. That's using Kirchhoff's laws. I can come around here to this point and get the exact same relationship. So we need a little bit more relationships. And that's the only one we're going to get from Kirchhoff's first law. So now let's look at Kirchhoff's second law. Kirchhoff's second law talks about going around in a path, around a circuit, a closed loop. So let's say we come out of E, we're going to travel this way, we're going to come through the L, maybe we'll turn down this way, go through the R, and then come back. There's one loop. Another loop would be, we're coming along here and suddenly we decide we're here at I3. We travel this way through I3, we come through this capacitor, and maybe we come back up through IR and back to where we started. So we're going this direction to this one. There's actually a third one, if you want to see it, and you can use any of the ones you want. Doesn't matter which one you do. We can come out of E, come all the way around and go through this capacitor, and then come back to E this way. So there's 3 different loops we can look at. We're going to go ahead and pick either one of these 2. We do need to probably have 2 loops we're looking at because we do branch off with 2 of them. So we have to include both of those. I don't care which ones we use, but I'm going to go ahead and use this blue one here and talk about what we're traveling through here. So when we start traveling, we come through E. So we gain it because we're going through it, we're traveling through it in the positive direction. We then come along and we're going to go through this inductor, and this inductor again stores charge. It's going to have a voltage drop, so it's taken away. So that's why it's minus, because it's taken away some voltage. Remember, E is voltage. It was added in. We're now taking away some voltage going through here, and it's saving some current. So and this is I1. So it's di1 dt. We then decide we're going to go through this blue one. So we're going to come down through I2. We're going to come through this resistor. Anytime we go through a resistor, we also lose voltage. So it's minus. So it's minus R1 times I2 because we're now through I2. We're now traveling I2's route. Then we come back to where we started. So we get 0. Our other one here, and it doesn't really matter where you start. Let's say we start here. We're going to come along here. We're going to travel along this route, and we're going to come through this capacitor. So when we come through that capacitor, the capacitor is storing your charge. And so the voltage drop through a capacitor is your charge divided by your capacitance. It's minus because it's taking some away, and we're traveling along this current. Now we come along, we're coming up through our resistor. And since we came up through it, it actually is adding because it's fighting the current. The current's going this way, which is where we'd lose it, but we're going opposite the current. So we actually gain going through that current, and it's R times I2. And then we get back to where we started, so that equals 0. So there's our 2 equations. Sounds great. Everything looks good, except we have too many variables. We have an I, we have an I2. And we have our Q. So we have way too many variables going on here to be working with. And we need to figure out how do we solve this problem and get through something with this to simplify this a little bit. So let's see if we can't come up with some kind of way to simplify this and get rid of some of our pieces. So one thing to remind you is that one thing to remember is that current is the change in charge. It's a storing of charge. That's what current is. Current is the rate of change of charge. So my I3, my current 3, is going to be, well, actually, let's quickly, before we do that, we'll do that in a second. But here, I'm going to go ahead. I'd like to get rid of my Q. So let's solve this for Q. So if I solve this equation for Q, Q would equal R over C times I2. Cool. So we have that. But again, we don't want to have current and charge and going on together. So one of the things we need to remember is how does current fit into it? So remember, I3 is going to be the rate of change of current, the rate of change of charge over time. So I3 is dq dt. All right. But Q, we just found out what it was. Q is equal to R over C, I2. So we're going to take the derivative of Q, which was R over C times I2. Well, R and C are both constants, so they can come out of your derivative. I is not. I is changing. Your current changes because we lose some of it going through different pieces. We have some voltage changing happening. So your current is changing. So it's not a constant, so it is going to have a derivative. So di2 dt. That's what I3 is equal to. All right. So now let's see what we have. We had this equation, E minus L di1 dt minus Ri2 equals 0. There's one equation we have. We now have this kind of other equation, well, that we can work with. Well, we have this other equation right here. I3 is equal to R over C di2 dt. So therefore, we can actually think of that one as being R over C di2 dt plus I3 or minus I3, because we are going to take them to the same side. So now we have our two equations. We're almost done, except that now we have I1, I2, and I3 in this equation. So it'd be really nice if we didn't have that many i's. It's okay to have two of them because we have a system of two equations. So it'd be nice to have two of my unknowns, but it'd be nice if we can get rid of one of them. So remember, I1 was equal to I2 plus I3. But I3 is right here. So if I could solve this for I3, in fact, I3 is I1 minus I2. So we now have E minus L di1 dt minus R I2 equals 0. And we have this, oh, I have R over C. I'm sorry. That wasn't R over C. That was R times C. I didn't notice I had made that mistake because C, we had to multiply both sides by C. So this is R times C. So we have now, we'll fix this. Sorry about that. So the other equation we have is RC di2 dt minus I1 minus I2 equals 0. So we basically now have our system, two equations and two unknowns. We have an I1, we have an I2, rate of changes going on here. We have I1 and I2 involved in these. The last thing we might want to do is get our derivatives together. So we have L di1 dt plus R I2 equals E. So get the derivatives, the dependent variables on the same side and get our constant on the other side, constant function, I should say. And then this one was RC di2 dt minus I1 plus I2 equals 0. And so here's our system of differential equations. If you want to, you can actually get the IDTs by themselves and get them on the other side. And so this is how we can get these together and create these systems, these models. So we aren't going to talk about how we solve them. We could look at graphically what they would look like, but this is just how we come up with these. This is not always the same. You would have to look at each one of your circuits you deal with to come up with it.